Good day, everyone. Today we will explore the different probability distributions that are commonly used to understand and predict outcomes in various situations. These distributions include the following: uniform, binomial, negative binomial, hypergeometric, geometric, Poisson, and normal distribution. Throughout this report, we will provide practical examples of each distributions to help you understand their applications and importance in different fields. So let's start with the examples of uniform distribution. So our first example is, suppose you roll a first six-sided die, what is the probability of rolling a 3? Since each outcome has an equal probability of 1 over 6, the probability of rolling a 3 is 1 over 6. So, as simple as that. Then, we have here another example. A random number between 1 and 10 is chosen. What is the probability that it is an even number? Since there are 5 even numbers, namely 2, 4, 6, 8, and 10 out of 10 possible outcomes, the probability is 5 over 10 or 1/2.
Now, let's proceed to the examples of binomial distribution. Our first example is, we have a basketball player with a free throw success rate of 80%. If she takes 10 free throws, we want to calculate the probability of making exactly 8 of them. Using the binomial formula with the given values of n equals 10, where it is the total number of free throws, x equals 8, where it is the desired successful free throws, p equals 0.8, where it is the probability of making a free throw, and q equals 0.2, where it is the probability of missing a free throw. We can calculate the probability. The probability is calculated as 10 combination of 8 times 0.8 raised to 8 times 0.2 raised to 2, which is equals to 0.302 or 30.2%. This means there is a 30.2% chance of the basketball player making exactly out of 10 free throws. An example goes this way. We have a multiple choice test with 10 questions, each having 4 choices with only one correct answer. If a student guesses on each question, we want to calculate the probability of getting exactly 7 correct answers. Using the binomial formula with the given values of x equals 10, where it is the total number of questions, x equals 7, where it is the desired correct answers, p equals 1/4, where it is the probability of guessing the correct answer, and q is equal to 3/4, where it is the probability of guessing the incorrect answer. We can calculate the probability. The probability is calculated as 10 combination of 7 times 1/4 raised to 7 times 3/4 raised to 3, which equals to 0.266 or 26.6%. This means there is a 26.6% chance of the student guessing exactly 7 correct answers in the test. Now, let's proceed to the examples of negative binomial distribution. We are surveying people exiting from a polling booth and asking them if they voted independent. The probability that a person voted independent is 25%. We want to calculate the probability that we need to ask 15 people before finding 5 people who voted independent. Using the negative binomial distribution with the given values of k equals 5, where it is the desired number of who voted independent, x equals to 15, where it is the total number of people asked, p equals 0.25, where it is the probability of a person voting independent, and q equals 0.75, where it is the probability of a person not voting independent. We can calculate the probability as follows. This means there is a 5.2% chance that we need to ask 15 people before finding 5 people who voted independent. Now, let's proceed to the next example. A football player with a success rate of hitting goals at 70%. We want to calculate the probability that the player hits their third goal on their fifth attempt. Using the negative binomial distribution with the given values of k equals to 3 where it is the desired number of successes, x equals 5 where it is the total number of attempts, p equals 0.70 where it is the probability a goal, and q equals 0.30 where it is the probability of not hitting a goal. We can calculate the probability as follows. For combination of 2 times 0.70 raised to 3 times 0.30 raised to 2, which equals to 0.1852 or 18.52%. This means there is an 18.2% chance that the player hits their third goal on their fifth attempt. Now, let's proceed to the examples of hypergeometric. Our first example is, in a deck of 52 playing cards, what is the probability of drawing 2 aces from a hand of 5 cards without replacement? Solution. There are 4 aces in the deck. Using the hypergeometric formula, the probability is calculated as follows, which equals to 0.0654 or 6.54%. Now, let's move to the second example. In this example, we have a group of 20 employees, 8 of them being managers. We want to calculate the probability of selecting exactly 2 managers when 4 employees are chosen at random. The hypergeometric formula, we can calculate the probability. There are 8 managers in the group, so the probability is calculated as follows, which equals to 0.3273 or 32.73%. This means there is a 32.73% chance of selecting 2 managers when 4 employees are chosen at random from a group of 20 employees where 8 of them are managers. We'll be discussing the examples of geometric distribution. Our first example is the basketball player has a 70% free throw success rate. The probability of making her first successful shot on the third attempt is calculated using the formula. 1 minus 0.70 raised to 2 times 0.70, which results in the probability of 0.063 or 6.3%. So, second example, the golfer has a 90% chance of hitting the fairway with each drive. We want to calculate the probability that they hit the fairway for the first time on the fifth drive. Probability of hitting the fairway with each drive is 90%. Number of drives to hit the fairway for the first time is 5. Using the geometric distribution formula, the probability is calculated as 1 minus 0.90 raised to 4 times 0.90, which equals to 0.0009 or 0.09%. Therefore, the probability of the golfer hitting the fairway for the first time on the fifth drive is 0.09%, given their 90% chance for hitting the fairway with each drive. Now, let's proceed to the examples of Poisson distribution. Our first example is, on average, there are 2 earthquakes per month in a certain region. We want to calculate the probability of having exactly 1 earthquake in a given month. So, solution. We have here the given values. Average number of earthquakes per month is 2. Desired number of earthquakes is 1. Using the Poisson distribution formula, the probability is calculated as follows, which equals to 0.2707 or 27.07%. Therefore, the probability of having exactly 1 earthquake in a given month based on an average of 2 earthquakes per month is 7.07%. Move to the example 2. On average, there are 5 car accidents per day on a certain road. We want to calculate the probability of having exactly 3 accidents on a given day. So, solution, we have here the given values. The average number of car accidents per day is 5. Desired number of accidents is 3. Using the Poisson distribution formula, the probability is calculated as follows, which equals to 0.1404 or 14.04%. Therefore, the probability of having exactly 3 car accidents on a given day based on an average of 5 car accidents per day, 14.04%. Now, let's proceed to the examples of normal distribution. Example 1. The scores on an exam are normally distributed with a mean of 65 and a standard deviation of 9. We want to find the percentage of scores that are less than 54. Given values. Mean equals 65, standard deviations is equal to 9. To calculate this, we first find the z-score using the formula z equals x minus mean divided by standard deviation. Plugging in the values, we get z equals 54 minus 65 divided by 9 equals negative 0.122. Next, we use the standard normal distribution table to find the cumulative probability associated with the z-score. In this case, the cumulative probability for z equals negative 1.22 is 0.1112 or 11.12%. Therefore, the percentage of scores that are less than 54 is 11.12%. Now, let's proceed to each of scores that are at least 80. To calculate this, we first find the z-score using the formula z equals x minus mean divided by standard deviation. Plugging in the values, we get z equals 80 minus 65 divided by 9, which is equal to 1.67. Next, we use the standard normal distribution table to find the cumulative probability associated with the z-score. In this case, the cumulative probability z greater than 1.67 is 0.0475 or 4.75%. Therefore, the percentage of scores that are at least 80 is 4.75%. We want to find the percentage of scores that are between 70 and 86. To calculate this, we first find the z-scores for the given values. For 70, the z-score is equals to 0.56. For 86, the z-score is 2.33. Next, we use the standard normal table to find the cumulative probabilities associated with these z-scores. The cumulative probability for z less than 0.56 is 0.7123, and the cumulative probability for z less than 2.33 is 0.9901. To find the probability between 70 and 86, we subtract the cumulative probability for z less than 0.56 from the cumulative probability for z less than 2.33. This gives us 0.9901 minus 0.7123, which equals to 0.2778 or 27.78%. Therefore, the percentage of scores that are between 70 and 86 is 27.78%. In conclusion, probability distributions are essential tools that help us navigate the complexities of uncertainty and make informed decisions based on data and probabilities. By studying and understanding these distributions, we gain insights into the likelihood of different outcomes and can make more accurate predictions. So that's all. I hope that you learned something.